Hello, and good morning to Percona Live Online 2021. This presentation is about comparing Percona XtraDB Cluster and Percona PS with the Group Replication and see how they fit in the an environment, in an architecture that we designed for high availability and disaster recovery. My name is Marco Tusa, and I'm the MySQL tech lead in Percona and principal architect. So what we are going to cover in this presentation is the overview of the concept high availability and DR, and then what kind of issue we mainly have when that high availability and DR should try to cover, and how PS with Group Replication PXC are able to cover those needs, and what kind internally, how they functions, and what there are similarities and where there are some difference. I'm very high level, not going into the technical details, and I'm not going to compare performance in this page. So why high availability? Of course, we have the OVH Inferno that represent one of the cases where obviously having a better structure of high availability and disaster recovery will help. I have been a witness of the negative impact because my internet service provider was having the platform on the OVH servers, and they lost everything for more than 7 days. Also, when they recovered the servers, the data was obsolete, and several issues. So having a good high availability and disaster recovery will help a lot in this case, right? Now, browsing around, because I was composing the slides for the presentation, browsing around, I found this graph that I think that is still very useful, and to understand, in one shot, what are the many events that could happen. That are not all, but it's still valid. It comes from an old Oracle 9 documentation. And as we can see, we go from natural disaster to human error to failure on a device, all things that could regularly happen. But when we talk level of high availability, what we are referring to? When we talk about high availability, we have the famous 9 or infamous 9 calculation, which is mainly given a specific period of time in the database world, we consider the high availability in relation to the uptime that the service provides. So given and a specific amount of time, it could be a days, week, or month, or a year, we do the calculation on how much in seconds, milliseconds, minutes, or hour, this will reflect the percentage of up and running. For instance, in 99.995 is just 4.32 seconds downtime per day, which is a glitch at the end, right? So it's just nothing. It becomes something like a downtime per year, that 26 minutes, which is obviously something larger. But considering the small part of the day is really nothing. It's just a glitch. In Percona, we do not consider high available a solution that unless they have at least 2.9 minimum. That's really we should consider high available that, but it's really the minimum thing, and it normally is not advisable to go for that. We normally suggest, when you ask for high availability, we suggest at least 4.9. Now, high availability. What is the coverage of high availability? The high availability is to be considered a solution that provide as I said, the coverage for having the system up and running in a local situation. So, when we talk about a data center or something that is distributed in a very close geographic area, for 1 gigabyte, 10 gigabyte Ethernet network, you have normally 400 meters in terms of radius, in terms of distance. After that, you start to have some kind of performance degradation. So the system needs to provide needs to be able to provide the service constantly in a very described and limited geographic area. While disaster recovery is exactly the opposite, right? It needs to be far, far away in order to be able to cover eventually major events like earthquakes and power grid or whatever, revolutions, something like that. In terms of solutions that provide one or the other, we have the tightly coupled cluster, which is in our case covered by PXC and Percona service with group replication. They both implement virtual synchronous replication, which is exactly that, a tight way to keep the data consistent between the nodes. While when we talk about DR, we talk about loosely coupled clusters, and this is covered by standard asynchronous replication. Percona implements for MySQL has this PXC and group replication with PS with group replication have the two different solutions in the Percona distribution. The Percona distribution is a set of packages that are tested in Percona and proved to be working correctly together. So a version, each version is tested and is certified to be working as it should. So instead going around and downloading Percona here, HAProxy there, and having possibly conflicts because the versions do not talk. If you take the distribution, you have all the things you need there, and you will be able to roll out your architecture using that. Now let's start to dig in a little bit in how PS with group replication and PXC works. Both cluster are cluster, right? and they actually use multiple nodes. Now, group replication comes with a default of single primary. The concept of single primary mainly is of the many nodes I have, I elect one node to be the focal point for writes. And then we have the concept of multi-primary, which instead is to distribute the write on multiple nodes. PXC comes with the concept of multiple writer, but then you can logically elect one of the writer as the primary. So it's not something that is inside the cluster itself, or like group replication, but it is possible to achieve the same thing at a higher level with HAProxy or Proxy SQL and electing, the primary artificially, logically. What is the benefit of having multi-writers, multi-primary? Actually none, because when you write on multiple nodes, again, each node will have to resolve the conflicts with the other writers and with the other nodes. And that means that each node will have to work harder to do certification and eventually roll out what they're doing. So the benefit is non-existent at the end, really. It's a more heavy load than anything else. While in all this, we need also to consider that writing in multiple nodes doesn't scale the writing at all. I mean, this kind of cluster scale only by read. And this is also important for the composition. When you start to build up a cluster, when you start to build up a cluster, you should start with the minimum requirements and then eventually add nodes in respect to the read factor. What does it mean? I have a minimum nodes for both solutions of 3 nodes. So let's start with 3 nodes. Let's select one node as primary, and then on the basis of what is needed, I will add other nodes in the cluster. Not for the write, because as I said, it doesn't scale right, but for the read. The advisable is to have always odd number of nodes in order to facilitate the calculation of the quorum, and how we will see later on, having even number of nodes can generate split brain and other things. But that is later on something that we will see. The cluster works. Both cluster works, and this is interesting because more or less, as you can see, they are going in parallel. The implementation may be different, the elements that they use in the implementation, but the functionalities at the end are very similar. So also in this, the clusters work, the solutions work building up a view. A view is the representation, the logical representation of a set of nodes that compose the cluster in a specific moment. So when I start the cluster and I initialize it, I have view 1 and this node 1, right? Then I add the second node and I change the view ID and I change the view composition. I'm showing here, for instance, an example of 3 nodes. I call it view ID 1 just to simplify. And the cluster uses this to also identify if something is starting to work not efficiently. Each cluster has health checks in communicating one node with another. And what happens is that whenever they start to see a node that is not working efficiently, they mark the node as suspicious. When the node is suspicious, it's still part of the cluster, it's not ejected, right? It's still part of the cluster. If the events resolve itself and the node start come back alive, let's say, come back and become 100% active, nothing happened, the cluster remains as it is, and all the work proceed as before. While if you have the node that continue to be unresponsive, then is automatically marked as to be ejected from the cluster. At this point, the cluster will need to re-elect, recompose the view, rebuild the quorum, rebuild the whole configuration, and see, okay, yes, I'm good to go ahead. If the node that was expelled wants to come back, at that point has to go back to the acceptance phase. So he needs to check the status that he has stored locally, verify if he can join and what is the distance from the other nodes, and he start to request the status and start to request the preset that are not applied locally, and so on and so forth. And the change, and obviously the cluster will change the view again, right, from 2 to 3. Now, for failure detector, for instance, split brain, I was mentioning that before. So everything is composed by, is based on the view. That is a very important element for the calculation, also the split brain. And for PXC specifically, there is a very strong message saying always build the cluster using an odd number of nodes, so 3, 5, and so on. Group replication is less, this advice is not really strong, but is better for you to go on the same way. Also, if the quorum calculation is different between the two. And in PXC, we have the quorum calculation based on all the nodes participating and the weight. So you can eventually play with the weight in order to have several or certain nodes to be more relevant than others. In group replication, that is not working like that. Is mainly the majority of nodes that can compose the cluster will say, yes, okay, we are good and we can rebuild a view for the cluster composition. Anyhow, when you have, let's say, a cluster of 5 nodes, and you have 3 nodes in data center 1 and 2 nodes in data center 1B, which is just around this across the street. And what happened is that if you have a network partition, then the 3 nodes obviously will be able to survive, and the 2 other nodes instead will be, declared as expelled by the cluster. But what happens if you have 2 and 2? At that point, if you have two nodes and the same event happened, the nodes will refer to the previous view and say, hey, wait a second, I'm two, was the previous view? Well, it was 4 nodes, we are 2, so there is not the majority in respect to the previous view, and the whole cluster will put itself on hold in order to allow a DBA to manually take action and eventually do some kind of operation. Or you can have 3 nodes on 5. You can have 3 nodes just crashing because the whole data center crash, like the OVH case, the main data center crash, and the other DC1B is still alive, but has only 2 nodes. What you can do? Well, in both classes, there is the way to eventually make them restart with force members for group replication and other, and also for a PXC in order to push it. But that is, always required DBA checking. Should never be something automatic. There are, so this is it. There are some technical things that I can add, but I want to keep the overview, not going in too much in the detail, just comparing how they can behave eventually. Now, transactions and how the apply flow works. I was talking about virtual synchronous, okay, virtually synchronous. Why not synchronous? Because synchronous is when I have the writer that does the commit finalize, and I have also the secondary that does the commit finalize at the same moment. Okay, so everything is synchronous in the operation when it is finally committed. This doesn't happen in group replication, doesn't happen in PXC. Both of them use a moment of a synchronous commit, and it works more or less like that for both. Again, the implementation can be a little bit different, but the effects at the end are the same. I got the writer, the primary, and who goes the write. It will start to perform the local operation, then commits. It replicates to the nodes. Then there is the certify phase. The first certify phase said, okay, you can go ahead. At that point, the primary will do the commit finalize. But the secondary nodes are still in apply. They are still applying. And then after apply, the commit finalizes. So that moment is asynchronous, okay? And this is exactly the same for PXC and group replication. Yes, there are moments that, the graphs are very similar, the way of interaction are similar, not the same in the implementation, but they're very similar. And as you can see also in group replication, there's local execution, consensus certified, it will push to the bin log and then commit. While on the secondary, the receiver is the relay log, and then they apply and then bin log and then commit. So it's, again, a synchronous process. The other important part is that when a cluster starts to receive a lot of load, you may have one node that is not able to cover the traffic as well as the primary. It happens, right? Also, if you have configured everything in the same way, it happens that you have some moment of congestion or something like that, and a node start to delay in respect to the primary. If this delay become too much, then the node raise a flag and ask for the cluster to slow down. This is the flow control in 2 words. In the implementation of flow control is completely different between group replication and the PXC. First of all, let's check PXC. First of all, the flow control in PXC acts in a different way in respect to the status of the node. So when the node is just open, no flow control, then it it join the cluster, and so when it's joiner and donor, there is a set of parameters that can be tuned in order to facilitate the communication to this node to recover the write set that are pushed by the primary, and at the same time to prevent the cluster itself to go too fast in order to not, which will be probably not allowing the joining node to join, because it will be constantly trying to catch over the primary. And then there is the joined that moment that is again a limited rate on the joiner that to facilitate the joiner that can apply. And then finally there is the sync when it is fully synchronous to the rest of the cluster. At that point, the node part is completely and fully part of the flow control mechanism. When it's synced, the node has, the node received the write set and put the write set from the primary in a receiving queue. When this receiving queue exceed a certain number of events, of elements, then the node, the secondary, will raise the flag saying, hey, I need to slow down. By default, if I remember correctly, 16 elements, but that could be obviously 2. But the more you increase the queue, the more certification effort that will require. So it's something that needs to be tuned carefully, but at the same time, you don't want to have a queue that is too large. And the other part is that when you have a flow control, when that happens, the flow control, the cluster will start to reduce the load. And if that happens constantly, the node is not able to catch up in a decent way, then you can also have a full stop from, the cluster will just hang waiting for the nodes to catch up and then reopen the channel. This is very impactful, in fact, and one of the problems we saw more often. While group replication works in completely different ways, not against a specific number of inside the queue, but is a set of statistics that are calculated inside the node. Each node calculates its own statistics for a specific amount of time. By default, this amount of time is 1 second. And the statistics are based on X number of parameters. And here we have few like queue sites, applier queue sites, and transaction, certified transaction, apply, and so on. The important part here is that when a node starts to see that is, when the node sees it's okay, say, okay, I'm good and can go on. When it starts to see is starting to have problems in applying with the same rate, it will raise the flag and say, hey, to the cluster, hey, I need to slow down. The slowdown that will happen is a percentage of the load that has been calculated in the previous view. So if I have done on an X number of operation, the cluster will try to slow down the percentage that is declared in the by default 50%. That is declared in the parameter whole percent, and it will reduce the load. As the same thing when same way when the node is okay to go ahead, then there will be a release, and the cluster will increase the percentage of in relation to the percentage of the transaction applied from in the previous example. Now, the control period, which is 1 second, is good when you have a good traffic that allow the cluster to do calculations. But sometimes you do not have enough transactions, and that in that case, the calculations are done on the nodes are not good enough to be efficient for the calculation, and you may have some weird behavior here. So the advice is, when you see that there is a very low level of activity, increase a little bit the control period, like instead 1 second, 2 seconds, or 4 seconds, 5 seconds, depending on you. But it's tunable. That is very important. And this, as you can see, the two flow control works in a completely different way. Now, Message fragmentation. What is message fragmentation and why exist? There is a the cluster checks the status of each node, right? And constantly there is this messaging going back and forth that say, hey, how are you? And when you have very large transactions, or when you do very heavy operation like data load, this message exchange can actually be delayed until when the cluster see the node that is busy as unresponsive. At that point, it is going to be marked suspicious, and in the worst case, also marked to be expelled. And that is bad, because actually the node is working, it's just busy. So the message fragmentation has been implemented. For PXC, we have two solutions. One is for specifically for data load, so for load data into whatever. And it has a configurable variable, but it comes with 10,000 rows per chunk. If the data load, of course, exceed that, you know, the cluster will create, the node will create chunks, and in the meantime will answer, you know, first chunk, second chunk, and answer to the cluster, I'm here, I'm good. And the second solution is the streaming. When you have a very long transaction or very heavy transaction, then you can use streaming replication. That is at session level or a global level. So you can configure globally, you can configure by session. The suggestion is to use by session, given the fact that you know, normally you are not supposed to have very heavy or long transaction. That is not always true, but you know, normally this is the standard. So by session, you just declare the fragment unit and the fragment size, which could be write set, row, or dimension, or bytes, and then how many. And you actually have the cluster, the node fragmenting and sending, you know, by sending the message to the other node, while be able also to answer to the others, to the cluster request, and at the same time is optimizing the transmission itself, right? In group replication, the message fragmentation is supported by 8.0.16 and after. So if you have a cluster that is below that version, you will not be able to support, or if only you have one node in the cluster that's below 16, that will not be able to support. It's a global variable that manage the message fragmentation. And the message delivery is complete when all the nodes receive it. The other part that is interesting is that if you have a node that is actually working in the cluster, then it gets expelled for any reason. And when it rejoins, it can reclaim the message from the other nodes. And it needs to get, of course, all the message back. Otherwise, the cluster will reject it. Now, data consistency. Both clusters certificate, you know, the write set when they receive it, do the certification phase. But that is actually not preventing the cluster to have internally data, different data by node. There is no the concept of single data store, you know, is actually distributed data store per node. And the cluster itself doesn't certificate each tuple in the node. Is not able to see if there is some kind of data drift. And in our experience in Percona, we have seen this happening several times. It could be for a malicious act, it could be for other operation happening during the maintenance, or it could be whatever, but it happens. Sorry, it happens a lot. Well, not a lot, but it happens. We have so many years, we have several cases. Now, this means that the cluster per se is not allowing you to, is not checking the data. And at the same time, this is for both of them. And at the same time, this is the part that are annoying me a lot. At the same time, it doesn't prevent the user to do stupid things. Actually, it allows the user to do stupid things. And I will show you now exactly what. There is also another part that is interesting, that when, of course, a node is being discovered as inconsistent, it got expelled by the cluster to allow the DBA to check. And this is a brutal kick out of the node at the end. Recently, in Galera, we had development that have developed a new protocol that is cluster error booting, that will make this process a little bit more consistent and solid, and allow the cluster to behave a little bit better than just kicking out the node. Anyhow, the two parameters that are that I will use here to show you how easy it is to corrupt data in a node are WSRep on for PXC and set SQL bin log 0 for group replication. Let's start to see. I have a cluster of 3 nodes, and then I have the primary writing on and distributing the writes to all nodes. Then what happened is that on junior DBA or someone with malicious intent connect to a secondary node, it just set WSRep on 0 and change the write set, the data on the table, adding records. I did then change back to set WSRep on 1, and after that the primary continued to push data on the same table, and it tried to write on that specific node. It tried to write in a row that already exists. At that point, the node say, no, I can't. Now, before, as I mentioned, before the cluster error booting, the node at this point will be expelled, and period. No information in the remaining nodes, just on the expelled node. So it also a little bit difficult at the beginning to debug what's going on. With cluster error booting, actually, we have the node instead just being out of the cluster. The node will say, hey, wait a second, I have a problem here. I cannot apply. What do you guys think? If the other nodes say, yeah, no, we're okay, what will happen is that the cluster will be change the view, will go ahead with the 2 nodes that are okay, and the node that has a problem will be gently expelled. Information about the work process is written in all the logs of the node, so it's easy to debug, and the DBA at that point needs to manually fix the data discrepancy on the node that is expelled. The same thing actually happened in group replication. And the only change is that instead of WSRep on, it will be used the SQL bin log 0. And it happens exactly the same thing. Yes, there is super read only set on, but again, I need to stress this. When you are able to do this kind of operation, or when very often it's because you are also able to circumvent this kind of limitation in action. Of course, it's safer than WSRep on, but it's still, something that it could happen. And in any case, this is just a manual action, but we have seen data drift happening for others or for other operation done through replication that makes things very weird. Anyhow, I set SQL bin log 1, and then the primary writes, and my node is having problems, and at this point it got expelled directly because there is no cluster error voting mechanism here. The other problem with consistency is when we have serve reads. The cell reads but sorry, the two solutions, both solutions come with settings that allow the cluster to have stale read. Stale reads happen when I have writes on a node and I'm trying to read on another node, in order to, and I'm looking for the same data while actually the data is still not applied because the virtual synchronous mechanism, right? So it's not fully synchronous. There is a moment of virtual synchronous. And this, we have seen this happening very often, especially when you use proxies, because the connectivity can change from very quickly, and from one operation to the another. And if the application is actually done in a way that it does in one transaction, then actually immediately after try to retrieve the node again, the information again. So it stale reads happen constantly, to be honest, and is something that you should not underestimate as well, because this is the graphs represent some testing have done, and if you do the testing on a medium load environment, you can see that for PXC, for instance, we have trying to write and read from another node, we have almost 50% of the operations there are stale reads. While for group replication is around 8 in average %. Now, it is notable here, and I have to mention that if you increase the load from medium to high, group replication just jumped from 8 to 50 as well. So it is really just a moment of, when the node incremented the load, they start to have problems, and well, more than problems, started just busy, and then still jump to the sky. Now, of course, if you instead set the parameters that in order to enforce to have consistent reads, you have 0 on both solutions, right? It just changes WS rep sync weight or change replication group replication consistency. Boom, perfect, nothing happened. And the impact in terms of time is also interesting here, because the impact, again, with a medium load for a PXC is just 5–6%, taking just 5–6%, a little bit more in terms of cost of time for executing the operation. While in a group replication is higher, it's 35%, sometimes a little bit more. So here we have an area of improvement for Oracle to work in making this a little bit less impactful. And of course, why we have reads, why the solutions comes with these default settings. Well, performance, right? But as you can see, at least for PXC, it doesn't make any sense. 5%, 6%, yeah, is something, but is much more important to have in a cluster that is supposed to be fully consistent. It's more important to have consistent data than 5% performance loss, at least in my view, because that data is the more important thing, the consistency of the data. Otherwise, don't go for a relational database, go for something else. Another part where we want to analyze, and this is very different between the two solutions, is DDL. The DDL are, like alters, are part of the normal life of any DBA. And what happened here is that we have a completely different implementation. In PXC, we have two main mechanisms: TOI, total isolation order, and RSU. The factor that should help you to identify which one of the two you use is when you do compatible changes against incompatible changes. Incompatible changes are that change the table structure in a way that are, if you do in a rolling mechanism with RSU, that will break the replication, because the table structure in one node will be different, for instance, from the primary to a secondary. And then, trying to push the data will actually corrupt the replication itself, will break the replication itself, because the structure do not match. Well, if you have compatible changes like adding an index where the application is still not deployed, you can do that on using RSU in rolling the alter one node and the other node and the other node. The point here is that we do not have online DDL in PXC, and the other point is that when you issue a DDL, the owner of the process is the cluster, right? Is the cluster itself. So you do not own, you do not control the transaction per se, and you cannot kill it. And we have seen in support and consulting and managed service, in Percona in general, we have seen a lot, and unfortunately long history of issues due to DDL, to alters that are there for hours, sometimes days, and locking, rollback, failure that bring the cluster completely down. So it's a operation that is very impactful. So it's good to have control for it and be able to say, no, I need to kill the process. There is a good approach, and there is a different approach that is very well described in the link I inserted here, written by one of my colleagues, and it's called manual RSU. There are pros and cons there, of course, as usual, but I suggest you to go and read it because it gives you the well understanding of the problem. Of course, to save the day, we have PT online schema changes, usual, which actually does the changes that you require in a way that the cluster will continue to write. There is no impact, and only at the end there will be a moment of locking, because the temporary table that they use by online schema change will need to be swapped with the production table, and that of course will require a locking moment. Now, group replication works in a completely different way. Group replication, first of all, in theory, support online DDL. And I'm talking about now. I hope this will change in the future, right? And then the operation is done by phases. If I do whatever kind of alter I do, let's say that I'm doing an alter that is allow the cluster to do, in theory, online. So I'm adding an index. Adding an index can be an operation, takes 2 seconds, and it could be an operation that stay there for hours, right? So I raise my alter, specifying the algorithm and the method. So I want in place, no locking, and whatever. And I'm adding my index. The first phase is the primary will receive the alter, will execute the alter, and I can do all the writes, no problem at all. As soon as the alter is complete on the primary, it gets shipped to the secondaries. At that moment, a meta lock is raised, and all the writes are locked. You cannot write anymore. And it stays like that until the end of the slowest alter, of the alter on the slowest node. So it could be that you have 10 hours to do the primary where you can write, and then other 10 hours on the secondaries that you cannot write. Now, if you use incompatible altered, so you cannot do an online DDL, you have 10 hours on the primary that are locked because the primary, and then other 10 hours because the secondary. So it takes the double time. Not only, if you have a problem on the primary while the secondaries are applying, the cluster is not able to actually identify a new primary until the fastest node had done and complete the alter operation. Again, if this takes 10 hours, you may be without a promise for 10 hours. To save the day, again, with the online schema change, and you will be safe. But it's not good. It's annoying. There is a bug about that. I hope Oracle is investigating and is coming back with something that will help us to have a better solution, because this one is a little bit not satisfactory for in my view. Now, we have browsed around the two different solutions, where they match, where they diverge, how they behave. Now, let's see the stack. When I design high availability, I don't look only at the data layer, right? I'm looking to the whole stack. I'm trying to start from the applications. So I have redundancy on the application level, maybe using containers or whatever, so to be able to build and recreate easily the application node. Then I have the connection layer, which starts normally with something like a load balancer, or a physical load balancer, logical load balancer, or something like keep alive D that is installed on different nodes and concerted a virtual IP. Then you have a proxy layer that is responsible to connect to the data layer and eventually manage the connectivity there, doing read-write splitting or other functionality, depending what you need. And this is, at the end, the last layer is the data layer itself. And you can see that the rest of the structure more or less remain the same. And this is very good, because that allows us to replace one technology eventually with the other, unless we have problems with the application to support that, right? So it is good to be able to, we have more or less the same kind of activity, the functionalities. We see the difference in flow control or DDL are, the flow control is just the implementation is different. In DDL, the difference is big, but at the end, if you use Percona with the online schema change, that will behave similarly, so you will be impacted by that. And so it's important to be able to eventually be in the position to replace one technology with the other. And that's for high availability. Now for DR, instead, building up the DR, we need to be aware of the fact that both solutions claim to be one natively able to support one natively, but then in small letter there is written that you need to have a good network in order to do so. Now, as said at the beginning, DR is not just across the street. That is still in the high availability configuration. DR is across the ocean, like London and New York, or Frankfurt and New York, Sydney, something distributed, right? Very far. And pretending to have a tightly coupled cluster working on the one is looking for trouble. Because yes, you may have it work, but as soon as you start to have load that is actually a significant load, the cluster and the network is unstable, and on the internet is by default unstable, you will have problems, period. No discussion about it. Unless you do one transaction per second, then you will be safe, right? So how we can do the DR? Well, it's simple. We need to use asynchronous replication, as described at the beginning. The problem with asynchronous replication is that assuming we have DC1, DC2, DC1 is the primary data center, and DC2 is the replica. So source DC1 and replica DC2. I set up my primary node on DC2 to connect to the source on DC1. And what happens is that if something goes wrong on the node on DC1, like maintenance or it crash, then my connection for the replication will just disappear, and my DC2 data center will lose its will start to delay in respect to DC1. So what can be done? With PXC, we can, if we use, we have two solutions with PXC. We can use we have asynchronous replication, but using the auto failover mechanism. Auto failover mechanism is available from 8.0.22, PXC 8.0.22, and it is working more or less in this way. You can set on any node or all the nodes eventually, but do not activate all the nodes, just one node at a time. But you can set the connection to one from the replica to one source node, and then say, I have these other 2 nodes, 3 nodes, 4 nodes, whatever, as replacement if something happened to that node. And what happened is that if something happened to that node, of course, the node itself, the auto failover, will shift to another source and will continue to replicate. And that is already a huge improvement. But it will not cover if my node on my replica node on the DC2 crash. Let's say that I have configured all the 3 nodes to be eventually replicas, but again, I need to implement one node at a time. And if my replica node crash, I need to manually take action there, right? I need to manually connect and reactivate the replication from DC2 reading the source on DC1. Given this is asynchronous, you can do that, right? It's not huge impact. You can do it. Or you can use a very smart script written by my colleague Yves Trudeau, PXC Replication Manager, which is a simple script that allows to manage exactly this situation. You don't even need to set up auto failover. It does everything for you, the script, and it will handle the node that is replicating from the primary, and it will shift the node if it's failing on both the data center, and it works very efficiently and is designed for PXC, which, by the way, has a problem in respect to group replication, because group replication, as I was saying at the beginning, elect the primary, while PXC see all the nodes as the same. There is no internal mechanism to elect the primary. So it's more difficult to do the calculation and the checking about which node should become eventually the replica. Okay, so group replication instead. What is as I said, you can use auto failover mechanism. Same thing as for PXC, and the problem is exactly the same. But as I was mentioning, the difference here is that I know exactly who is the primary. So while we are waiting for MySQL to come out with an embedded solution, I just did a proof of concept. I wrote a very simple procedure that I call GR failover, and is available on my GitHub, which actually check the status of the nodes and identify the primary on the replica side and say, okay, are you active? Yeah, all good. Then if you see that the node is not able to replicate anymore because there is an epoch that is constantly refreshed, if you say that this doesn't work anymore, then we'll try to identify the next primary, the other primary, and we'll rebuild the connectivity there. Okay, so it will establish the connectivity there with and mainly the same effect from PXC Replication Manager, but simplified because we already have the primary election in group replication. So it's much simpler for us in group replication to decide who should be the replica. Now, in terms of adoption, we have the two products that PXC obviously is around from longer time, almost 13 years, if not even more, is the most suggested solution for high availability right now. And we have many years of knowledge, consolidated knowledge about how it works, what kind of problem it has, what are the most common issues. And given that, it's easier for everybody to interact with the product. So all these are very good points for PXC. For cons, a little bit cons, let's say that we have the fact that some of the new features are going to exist only in MariaDB Enterprise from CodeShape, and also the move to support on the GTID for coming from Maria, that is a different protocol that is absolutely not compatible with the others. Me being a community person, I personally feel uncomfortable with these changes, but that's me only. The other part is the code is shared as star. There is not visibility about the changes in the Git repo, so it's more difficult to interact with the code itself and to provide feedback and to provide an enhancement, and as open source normally is. Group replication pros are obvious, is one of the main core feature for Oracle, for MySQL, especially now for the cloud. So if you check in the cloud, you will see that the solution, almost all the solution, use group replication behind. And it uses well-known mechanism like GTID, binary log, and so nothing new here. Given that the base knowledge is very well consolidated, what we need to do is just learn the small part on top related, to the group replication itself and tooling about it. And Percona already has a good training for 101, Percona 101 for group replication, and we are developing the 201. So if you're interested. And code is available on GitHub. You can go there, you can read any single line, which is fantastic. You can download it, do some tests, eventually change the code and see all. The cons is that it's relatively new. It's only from 2014 where we had the Hello World in a presentation, I remember that. And the first almost ready production version was 8.0.20 from my side, from my point of view, but and of course the adoption is still limited. So we need to help in the improvement and the adoption. We need to promote this in order to be able through the community to suggest fixes, to identify additional corner bugs that are difficult to identify, and to make the product better. In terms of monitoring, both PMM, Percona monitoring and management tool has dashboards for PXC and for group replication. Group replication, we are enhancing the dashboard constantly. So what you see today, it could be better tomorrow, but they're there, and they are very useful to debug issues on the product itself. So in conclusion, and I would say that Percona support both PXC and group replication. As in terms of architecture, when we build the architecture, you can choose one or the other. The main structure of the architecture, the different stack will remain the same. It's really trying to understand which fit better your needs in terms of the database layer. And it's very good to have the two solutions. Of course, PXC is still a very strong solution and is not going to disappear or go anywhere. But at the same time, group replication is becoming better and better. And we really want to have that more adopted in order to be able to make it better as product, as community. And I think this is all. I will really appreciate any question that you will want to send to me, and I will answer asynchronously. Thank you very much, and have a nice day.